I am a second year electrical engineering student. Today I am presenting our project UAV based power line insulator classification. So, what is the problem? Manual inspection of power line insulators is hazardous and time consuming. It requires climbing towers or expensive helicopters. Since we have UAVs and they can capture thousands of high resolution images, but manually analyzing this data is impossible. So, our solution is an automated computer vision system to detect and classify insulator materials from UAV imagery. Since insulators are critical components of electrical grid, however, inspecting them is one of the most dangerous and slow jobs in the utility industry. While drones have made data collection safer, they generate massive amounts of visual data. Our goal is to solve this by using artificial intelligence to automatically identify and classify these insulators directly from the drone's photos. Different materials degrade differently. Identifying the material is the first step towards targeted and predictive maintenance. We didn't just want to detect insulators, we wanted to know what they were made of. We focused on three most common industrial materials: porcelain, glass, and composite. Because an engineer needs to know this. Porcelain cracks, glass shatters, and composites degrade differently under pollution. Classifying the material allows utility companies to plan specific cleaning or replacement schedules, which is vital for grid reliability. First step of our project is data acquisition, for which we downloaded the MPID dataset from its official repository. But these folders are not according to the YOLO V8 format, for which we had to merge all of the dataset. So we arranged our files according to this format. So our file has both training and validation sets. And each of the training and validation sets will have its corresponding labels and images. But if you download the MPID dataset, you have to make sure that your labels are correct, because when we downloaded the dataset, we noticed that our classes were not labeled properly, so we had to code the data again. The MPID Merged Public Insulator Dataset is an open source multi-type insulator dataset specifically designed for high voltage power line inspection using UAVs. The dataset is categorized into three primary material families: glass, porcelain, and composite insulators. It is a merged dataset, meaning it was built by combining several different public and private collections of drone inspection images to ensure high diversity in backgrounds and angles.
This is the code we use to merge our dataset. Import OS. This imports the OS module to work with the file paths and directories. Import shuttle. This imports the shuttle to copy files from one location to another. Source underscore dirs is equal to. This dictionary defines the dataset folders and assigns each class ID. Porcelain is class 0, glass is class 1, and composite is class 2. Target underscore root. This sets the main folder where the final merged dataset will be stored. Subsets. This defines the dataset splits, training and validation. This loop goes through each dataset folder and its assigned class ID. For subset in subsets, this loop goes through both train and validation data set folders. Source underscore image underscore path. This creates the path to the source's images folder. Source underscore lbl underscore path. This creates the path to the source labels folder. Dest underscore image underscore path. This creates the destination path for images in merged dataset. Dest underscore lbl underscore path. This creates the destination path for labels. This os dot makers dirs. This creates the destination label folder if it does not exist. These both os dot make dirs and os dot make dirs creates the destination label folder if they do not exist. If the source folder does not exist, it skips for the next iteration. This loops through all image files in the source folder. Shuttle.copy copies the each image from the source folder to the destination folder. This loop lbl underscore file loops through all label files in the source label folder. With open opens each label file and reads all lines. This creates new label file for the destination folder. For line in lines, this loops through each line in the label file. This parts splits the label line into parts based on spaces. If length of parts is greater than 0, this checks that the line is not empty. This replaces the class ID with the new mapped class ID. F.write. This writes the updated label line into the new file. Now we use print. This prints the message indicating the dataset merging file process is finished.
Then we are required to create data.yml file which has path. This specifies the root directory of the dataset where all the images and labels are stored. Train. This defines the training images folder relative to the root path. Val. This defines the validation images folder used to evaluate the model performance during training. Names. This section defines the class labels used in the dataset. Class ID 0 corresponds to the object porcelain. Class ID 1 corresponds to the object glass. And class ID 2 corresponds to the object composite. This YAML file tells YOLO where the dataset is located and defines the class labels used for training and validation.
Spartus model selection. YOLO V8N, which is the nano version of the YOLO V8 object detection model, is designed to be lightweight, fast, and efficient while still maintaining good accuracy. Its architecture is mainly divided into three important parts: the backbone, the neck, and the head. The backbone is responsible for feature extraction from the input image. It processes the image through convolutional layers and advanced modules like the C2F block, which improves feature reuse and the gradient flow, making the model more efficient. It also uses a spatial pyramid pooling fast SPPF layer to capture features at different scales. helping the model detect both small and large objects effectively. In simple terms, the backbone acts like the eyes of the system, identifying important patterns such as edges, textures, and shapes. Now let's see about the second part, neck. The neck of YOLO V8N is used for feature fusion, meaning it combines features extracted from different layers of the backbone. It uses a combination of feature pyramid network FPN and path aggregation network PAN structures to parse information both from top to bottom and bottom to top. This allows the model to preserve both detailed spatial information and high level semantic information. As a result, the model becomes better at detecting objects of different sizes, especially small objects that are usually difficult to identify. The neck essentially acts like the brain, integrating all the extracted information and enhancing it before passing it to the final stage. Now let's see about the third part, the head of YOLO V8N is the deduction layer where the actual predictions are made. It uses an anchor-free and decoupled design, which means it does not rely on predefined anchor boxes and instead directly predicts object locations. The decoupled structure separates the tasks of classification and bounding box regression, improving both accuracy and performance. The head produces the final output in the form of bounding boxes, class labels, and confidence scores for each detected objects. It also performs multi-scale predictions, enabling it to detect small, medium, and large objects effectively. Overall, the head acts like the decision making part of the model, providing the final detection results. The anchor free design is used because it simplifies training and allows for better generalization to various insulator shapes.
So let's start with training our model. Firstly, pip install Ultralytics. This installs the Ultralytics YOLO library required for training and detection. After this, we are mounting our Google Drive onto Colab. So this code imports the Google Drive module in Colab. It mounts your Google Drive so you can access the files that are stored in it. Results is equal to model.train. This starts the training process and stores the output in the variable results. Data is equal to, this specifies the dataset configuration file containing dataset paths and class labels. Epoch is equal to 100. This trains the model for 100 epochs, meaning the data is processed for 100 times. Image size is equal to 640. This sets the image size to 640 cross 640 pixels for training. Workers is equal to 6. This sets the number of CPU workers to 6 for faster data loading. Batch is equal to 16. This defines batch size as 16 images per iteration depending upon the GPU memory. This code trains the YOLO model for 100 epochs with optimized batch size and parallel data loading for better performance. So we can use this code if our model stops training at a certain epoch. So it resumes the training from where it has stopped. So now we can see how our model has trained for the first 100 epochs. Now we'll talk about the confusion matrix we obtained after 100 epochs.
At the end of 100 epochs, we have this confusion matrix. The confusion matrix is usually used to calculate the accuracy, precision, and recall, also an F1 score of the model. Here, precision focuses on quality, recall focuses on quantity, and F1 score focuses on balance. Diagonal element shows the correct predictions, true positives for each classes. Our model performs well when it comes for class specific performance. It is not confusing between glass and porcelain and composite. The precision is high. When the model does claim something as porcelain or glass, it is always correct. It rarely hallucinates object when there are none. Recall. It is moderate to low. The model is shy. It would rather say that's just background than risk making a wrong classification. MAP, mean average precision, likely impacted by the background misses. If the model fails to detect the object, the MAP score will drop significantly. Glass has an excellent quality precision and porcelain has a good precision. Even composite has a quite good precision. Overall, the performance of the model is good. In this, the only disadvantages is the background problem. The model hallucinates the background when there are none and also misses the insulators due to sunlight or many other conditions and hallucinates it as a background. In this, nearly 118 instances where an insulator was missed entirely. To overcome this, we have used the data augmentation techniques and trained our model for the next 50 epochs.
From Ultralytics, we import YOLO. Model underscore path. This specifies the path to the best trained weights from the previous training. Model. This loads the YOLO model using the saved best weights. Model.train. This starts the training process with custom settings. Data. This provides the dataset configuration file containing paths and class names. Epochs is equal to 50. This trains the model for 50 additional epochs. Image size is equal to 1024. This sets the image resolution to 1024 cross 1024 for better detail detection. Batch size is equal to 16. This defines the number of images processed at once based on GPU memory. AMP is equal to true. This enables the mixed precision training for faster computation and less memory usage. HSV underscore H is equal to 0.015. This slightly changes the hue of images for color variation. HSV underscore S is equal to 0.7. This adjusts the saturation to improve robustness to lightning conditions. HSV underscore V is equal to 0.4. This changes brightness, helping detect reflective surfaces like glass. Copy underscore paste. This copies the objects and pastes them onto different backgrounds to increase the data diversity. Mosaic is equal to 1.0. This combines multiple images into one for better object detection in various contexts. Mixup is equal to 0.15. This blends two images to improve generalization. Erasing is equal to 0.4. This randomly removes parts of images to help model the handle situations. IRO is equal to 0.005. This sets a low learning rate to make small stable updates. Here we used the optimizer Adam W for efficient training and better convergence. Project. This sets the folder where training results will be saved. Name. This creates a new subfolder with this name to store results. So we use the following data augmentation techniques to train the next 50 epochs.
After using data augmentation techniques and the end of 50 epochs, this is the confusion matrix we get. Here we can see there is an increase in the number of true positives compared to the previous confusion matrix. This shows the model has trained better and able to distinguish better. Postline has a 631 true positives showing a solid performance. Glass has a 808 true positives which shows a strong performance and a very high recall. Composite has a 183 true positives. This shows it is accurate when detected. The advantages of this is high material specificity. The model is excellent at distinguishing between different types of insulators. For example, there is almost zero confusion between porcelain and glass, and very little between glass and composite, that is only 3 instances. Strong feature extraction for glass. With 808 correct hits and relatively few false negatives, the model has clearly learned the visual characteristics of glass insulators effectively. Low interclass error. The crosstalk between the actual material classes is minimal, which is vital for industrial applications where material type dictates maintenance protocols. For porcelain, the precision is approximately 92.2% and recall is approximately 97.6%, showing a high recall. And for glass, the precision is 88.1% and the recall is 94.7%. Composite, the precision is 86.3% and the recall is 92.4%. From this, we can get to know it has higher interclass discrimination and a very high reliability. For an inspection project, the high recall is vital, that is low false negatives between classes. It means when the model sees an insulator, it is very likely to identify the material type correctly, which is essential for power line inspections.
Web interface is built using Streamlit, an open source Python framework. Its goal is to provide a real time web interface where a user can upload UAV inspection images and immediately see results without touching the underlying YOLO V8 code. So let's see how it works. So we can upload any of these images, and that is how our model has predicted porcelain. And then next we'll try to test on another image. So this is how our model predicts. This sidebar slider is used to set the confidence threshold. This allows the user to manually adjust how sure a model is before it flags an insulator.